So this is a video just wanted to run through, once again, finding the roots of a polynomial. So before we start on this, I just want to kind of summarize. We have what are called real roots. And those are broken into rational and irrational. And then we also have imaginary roots. Imaginary roots. Both the rational and irrational roots will show up as X-intercepts. Imaginary roots will not show up as X-intercepts. There will not be a crossing on the x-axis that corresponds to imaginary roots. So rational are numbers that can be expressed as a fraction. Irrational are numbers that can't be expressed as a fraction. So irrational would be like a square root of 2, for example. Any square root that you that's not a perfect square is going to produce an irrational number. So if you think about the quadratic formula, for example, if the inside of that thing is a perfect square, it'll produce a rational number. If the inside of that thing is not a perfect square, it'll produce an irrational number. And if the inside of the square root is negative, it'll produce imaginary roots. So imaginary roots are imaginary numbers. Imaginary numbers are based on the concept that I is considered the square root of -1. So up to this point, we've been talking about not being able to take the square root of a negative number, and that's still true. You cannot take the square root of a negative number and produce a real number. That's why we don't consider this. If you have to take the square root of a negative number, it's not a part of the domain, because the domain is just over the real number realm. So, but now we can talk about numbers that have negative x or negative square roots in them, because we've labeled this thing I. So for example, a number like 2 plus 3i is a number. It's called an imaginary number, but nonetheless a number. So you can have roots of a polynomial that are imaginary. The other thing to remember about imaginary roots is they always come in pairs. So if 2 plus 3i is a root, that means that 2 minus 3i is also a root. They always come in pairs, and they're called conjugate pairs. So an imaginary number, you have a real component, which is this part, and you have the imaginary component, which is the part with the I. So conjugate pairs have the same real component and the opposite imaginary component. So another example would be 5i and negative 5i. Or -3 plus 2i and -3 minus 2i. That's a conjugate pair, those are conjugate pairs, and those are conjugate pairs. And again, if you have an imaginary root, you'll never just have one imaginary root, you always have, they always come in pairs. So you could have 2 imaginary roots, or 4 imaginary roots, or 6, etc. You never have an odd number of imaginary roots. Okay, so coming back to here, this is a polynomial. We want to find the roots of it. Notice I could also ask you to write this in factored form. You do the same type of math, just the answer would be different. So let's find the roots first. So if we were trying to find the roots of this, first thing I would do is graph it. So I'd grab my calculator, hit the y equals button, and I'd type in 4x to the third. Minus 7x plus 3. When I graph it, I can see the graph crossing at, it looks like 1, somewhere between 0 and 1, and somewhere between -1 and -2. So 1 is an easy one to work with, so I'm going to throw a 1 in the box. And I'm going to set up my 4, and I'm going to put a 0 here because there's no x squared, -7 and 3. Okay, so then I'm going to run synthetic division. Add 4 to nothing is 4, 1 times 4 is 4, 4 plus 0 is 4, 1 times 4 is 4, 4 plus -7 is -3, 1 times -3 is -3, -3 plus 3 is 0. So that means that 1 is a root. And then we're left with 4x squared plus 4x minus 3. And that is, we know it's a quadratic. It's a second degree because we start with a third degree and divided once, and that'll leave us with the second degree. So then this is either factorable, or I can throw out the quadratic formula. I think this one's factorable, so we could do a 2x and a 2x and a 3 and a 1, and I think if we make that positive and that negative, it'll work. Because we got 6x and negative 2x gives me 4x. Yep. So that means the other roots would be whatever make these factors equal to 0. So if I plug a 1/2 in there, that would make that 0. If I plug a negative 3/2 in there, that would make that 0. And then my other root was 1. So the roots are those 3. So now, that's the roots. That would be answer this question. I could have also asked you to write that in factored form. So if you were to write in factored form, I'd write it as f of x is equal to, and I would just take the different factors. So that would be 2x minus 1, 2x plus 3, and the factor that goes with 1 would be x minus 1. And if you were to multiply this all back out, you'd get that polynomial. So that's in factored form, and I could have also asked you to find the x-intercepts. Well, the x-intercepts would also be the same as the roots, 1/2, negative 3/2, and 1. Okay? Okay, so here's another example. I've already graphed this and saw that it looks like it crosses at negative 3, so I'm going to try negative 3. So I put a little negative 3 in the box, and I put a 1, a 3, a 25, and a 75. And runs to the division, so that would be 1, negative 3, 0, 0 plus 25 is 25, and negative 3 times 25 would be negative 75. Which of course gives me 0. So that means that negative 3 is a root, and that leaves me with x squared plus 25, because that's like 0x there. So the other two roots are going to come from this. So I just basically have to figure out what makes this equal to 0. So that would be x squared is equal to negative 25. And that means x is equal to plus or minus the square root of negative 25. So now, this is where the imaginary number is talking about. So I'm taking the square root of 25, of a negative 25. So that means the square root of 25 is 5, and the square root of a negative 1 would be I. So this is really saying that the roots are negative 3, 5i, and negative 5i. So those are my roots. Okay, and just so we're abundantly clear, if I would have asked, we've answered that question. If I would have asked to write in factored form, then I would have taken so that negative 3 comes from the factor x plus 3. But I don't write x minus 5i, x plus 5i, because that's not proper factors. What we would do is write x squared plus 25. So what we have a linear factor and an unfactorable quadratic factor. So this would be that polynomial written in factored form. And finally, if I would have asked for the x-intercepts, just like I said earlier in the video, that imaginary numbers will not show up as x-intercepts, so the only x-intercepts for this are negative 3. So this graph only crosses the x-axis at negative 3. So essentially, if you graph it, it looks something like this, and there'll be some bump up here somewhere where it doesn't cross the x-axis. Okay? Okay, here's a fourth degree polynomial. And so I'm going to try to find the roots. When I graph it on my graphing calculator, it looks like it's crossing at -3. So I'm going to go ahead and try -3. It also looks like it's crossing between 0 and 1, which that might be 1/2 or 1/3 or something. So I'll check that out in a minute. But start with -3, and I put a 2, a 5, a 15, a 45, and a -27. Okay? So bring my 2 down. -3 times 2 is -6. -6 plus 5 is -1. -3 times -1 is 3. Be 18. -3 times 18 is what? 36, 40. Is that right? Maybe 30 plus, yeah, -54. And -54 plus 45 is -9. -3 times -9 is +27, and I get 0. Okay? And so there's 1. So now I'm dealing with a cubic right now. This would be 2x cubed minus x squared plus 18x minus 9. That's the bar there. And on the graph, it looks like it's crossing between 0 and 1. So I'm going to go ahead and try 1/2. And bring the 2 down. 1/2 times 2 is 1. That looks good. 0. 18 plus 0 is 18. And 1/2 times 18 is 9. And 9 plus -9 is 0. Okay, so once again, I'm ended up with a quadratic, which gives me 2x squared plus 18. And I know that -3 and -1/2, or -3 and 1/2 are two of my roots. This is going to produce 2 more. 2x squared is equal to -18, which means x squared is equal to -9, which means x is equal to 3i and -3i. So my roots, or zeros, root 0, same thing, are -3, 1/2, 3i, and -3i. Very nice. If I was to write this in factored form, again, this is not asked on this sheet, but I'm doing this to show you other questions I could ask. If I was to write this in a factored form, I would write it as, so I got -3, so that would be x plus 3. I have a 1/2, so that would be x minus 1/2. And I have a 3i and -3i. Now remember, that came from this guy right here, an unfactorable quadratic. So I'm going to write that 2x squared plus 18. But notice there's a factor 2 in there, and also notice that this is not really good factored form, because usually we don't include fractions in factoring. If you think about all the trinomials you've factored in the past, you usually don't think of throwing a fraction in there. So what we're going to do is factor 2 out of this. So really you'd write this as y equals x plus 3 times x minus 1/2 times 2 times x squared plus 9. And now that's fully factored. You can't really say something's factored if there's still a greatest common factor. And we're going to distribute that 2 through here. So what our end result is really going to be x plus 3 times 2x minus 1 times x squared plus 9. And that would be the true factored form. Okay? And then finally, if there's any x-intercepts, what are they? Well, the 3i and the -3 are not going to give us x-intercepts. So it would just be -3 and 1/2.